This map of the 30-agent landscape shows our current position in the software development tier. We are stepping away from code generation and moving directly into the domain of agent number 14, the security-hardened agent. In the previous chapter, we built an agent that writes code until it passes every functional test in the suite. It proves mathematically that the logic behaves exactly as requested. But in an enterprise environment, a function that executes perfectly can still be entirely illegal. Functional correctness is completely orthogonal to regulatory compliance. Picture a Python script that processes a customer's payment. The transaction goes through, the database updates, and the unit tests light up green. But in the background, the script quietly writes the full unencrypted credit card number to a plain text log file on the server. Standard testing pipelines will never catch this. Tests are designed to verify the outputs of specific behaviors. They are not built to enforce normative constraints, like the payment card industry data security standard. Traditionally, organizations rely on a human auditor to manually review code for these vulnerabilities. That means the exposed plain text file might sit on a server for months until an audit catches it, exposing the company to massive fines. As AI coding assistants accelerate development to machine speed, manual reviews become a dangerous bottleneck. If an autonomous agent is going to write and deploy code in minutes, it requires an autonomous immune system that asks, "Is this legally permitted?" before the code is ever allowed to merge. We have to move compliance from an auditor who arrives after the deployment to a bouncer standing at the door of the continuous integration pipeline. This diagram maps the architecture of that bouncer. Agent 14 operates on a continuous, 6-stage governance loop that intercepts every change proposed by a developer or an AI. The cycle starts at stage 1, the trigger. A GitHub Action or commit push instantly wakes the agent to evaluate the incoming pull request. In stage 2, the scan phase, the agent breaks the code down into an abstract syntax tree. It analyzes the data flow, tracing the exact path of sensitive variables, like our exposed credit card number, from the initial input down to the vulnerable log file. Stage 3 handles evaluation, and it uses a dual-engine approach. It runs the code against hard deterministic policies written in a language called Rego, while simultaneously using a large language model to evaluate the semantic intent of the developer's comments. You cannot rely on a language model's probabilistic guesses to decide if you broke the law. If regulators demand proof of compliance, you need the deterministic certainty of a strict policy engine. The LLM simply provides the nuance to catch malicious workarounds that dodge the rigid rules. Combining these two methods creates a defense-in-depth architecture. The deterministic engine catches the obvious structural violations, and the semantic model catches the hidden loopholes. Once a violation is confirmed, the architecture moves down into the resolution phase. At stage 4, remediation, the agent refuses the merge. It immediately synthesizes a patch, suggesting an exact fix, like applying a masking function to obscure the final 4 digits of the credit card. If the context is ambiguous, stage 5 routes the decision to a human-in-the-loop override. The human operator provides the contextual judgment necessary to clear the code or mandate the fix. Stage 6 writes every rejected merge, every proposed patch, and every human override into an immutable audit trail. This governance is enforced directly at the code level. Here, a raw Python logging command attempts to execute, but an active Rego policy detects the absence of a masking function and immediately terminates the process. The continuous integration pipeline serves as the final compliance gate. The flawed code physically cannot enter the production branch without satisfying the policy or securing a recorded human exception. By embedding policy as code directly into the CI/CD pipeline, organizations can mathematically guarantee that their autonomous engineering outputs align with strict legal boundaries. This same framework scales across heavily regulated industries. It enforces HIPAA data controls in healthcare, restricts cross-border data routing for GDPR privacy, and maintains strict infrastructure configurations for SOC 2 audits. But Agent 14 operates strictly on the rules you provide. It possesses no inherent common sense. If an organizational policy is not explicitly encoded into a Rego file, the agent will not enforce it. This leads directly into the third and final step of the software development tier, Agent 15, the self-improving agent. The bouncer's immutable audit trail serves as a high-fidelity dataset for the system's evolution. Every human decision to accept or reject a patch is captured and indexed, providing the specific training data required to refine the agent's baseline intelligence over time. Concluding, Agent 14 is the essential bridge that makes rapid, autonomous code generation safe enough to ship. To examine the complete LangGraph architecture and access the code for the Security-Hardened Agent, read 30 Agents Every AI Engineer Must Build by Imran Ahmad, and explore the full series at neuralsca.